We've just gone over these probability terms and results, and now it's time to do a few problems to illustrate them. So flip ahead about 2 pages, and you'll see some example problems. Let's take a look at number 1. So the probability of getting the big order under negotiations is 0.4. Well, the probability of losing money this quarter is 0.5. First thing you usually want to do with these is to write down what you're told and clearly identify the events. So let's go over to the whiteboard here and write down what we've been told. So let B equal the event that we get the big order. Remember that we usually use capital letters to indicate events. Then let L be the event that we lose money. Let's also keep track of the probabilities we've given. So the probability of B is 0.4, while the probability of L is 0.5. Let's read on. So in part A, we're told, assume that these events are mutually exclusive. And we're asked to find the probability of getting the big order or losing money. So let's go back to the sketch pad. And in part A, we're told that B and L are mutually exclusive. What does that mean? Well, what that means, if you remember, is that B, the probability of B and L occurring simultaneously, is 0. Now, let's go draw this. Here is the sample space. Remember that a sample space has an area of 1. So these things all have to add up to 1. Somewhere out here is an event B, which is 0.4. Somewhere over here is an event L, which has probability 0.5. So that's the picture of our sample space. Let's go back and read exactly what we have to find. So now find the probability of getting the order or losing money. So the word or right here is quite important. So if we translate that statement into symbols, the probability of B, now or gets translated into a union, B or L. How are we going to solve this? Well, hopefully this is somewhat obvious. It's just going to be the sum of the two, but we're actually going to use the OR theorem that I went over. So what is the OR theorem? The OR theorem says that this is equal to the probability of B plus the probability of L minus the probability of their intersection. So the probability of B intersect L. So let's just go plug in the numbers. 0.4 plus 0.5 minus 0, and the answer is 0.9. So the chance that we either get the big order or we lose money is 0.9. Let's read on. Part B, assume that these are mutually exclusive. Does this rule out the possibility that you fail to get the big order and make money this quarter? So there's an and in there. So let's write down exactly what this is asking about. Probability that we fail to get the big order is not B. And, let's see, and we make money this quarter. So making money is not losing money. So we're going to put not L. Now, if you think about it, we go over to our sketch pad. Let's try to just shade this in. So this area right here is not B. Now what is not L? Well, not L is this as well as this. So what we're really asked about is we have to have both types of shading, which is this area right in here. So what is the area of that? Well, it's going to be 1 minus 0.9. 1 minus 0.9 equals 0.1. Now, what we've just done is derived something called De Morgan's laws in doing this problem. So I'm going to go back to the bottom of that page. The bottom of the page has these De Morgan's laws, and what we just did was to derive the first one, namely that the probability that not two things happen, both of them happen, is just 1 minus the probability that either one happens. So these De Morgan's laws are really quite useful to us. So part C, Now assume that instead the events get the big order and lose money are independent, since I guess if we get this big order, it doesn't show up until the next quarter in our financial statements. So what is the probability of getting the order and losing money? Well, what you in general want to do with this is write down the implications of the given. So you're told that B and L are independent. Now what this means, remember there are three different implications of this. One implication is that the probability of B and L is now the product of them. So 0.4 times 0.5. So the probability of their intersection is 0.2. So that's just an implication of independence. If we go back to the problem, that's what we're asked to find. So what's the probability of getting the order and losing money? It's 0.2. It's probably worth drawing it. So if we draw it, this is B, and this is, say, L down here. All of this is L. And notice there is an overlapping region here which has probability 0.2. And then this would be probability 0.1 out here. That's what we've, no, I'll forget that. So that area in the middle is 0.2. All right, part D. Now assume instead that the probability of getting the order and losing money is 0.1. Are they independent? Well, how do you know? All right, so in part D, we're told to assume that the probability of B and L equals 0.1. So are they independent? Well, the way to do this is to go back to the definition of independence. So let's see. We know that this, under independence, is equal to, I'm just going to write it this way. So under independence, the probability of B and L both occurring, by definition, is the probability of B times the probability of L. So let's go write in the probabilities of B and L. Well, this is just going to be 0.4 times 0.5, and that's 0.2. Now notice that we've just formed a nonsensical statement. We're just saying 0.1 is equal to 0.2, and that can't be the case. So somewhere we made a mistake. Where did we make a mistake? Well, we made a mistake in assuming independence. So since these numbers are not equal, we conclude that B and L are not independent. And that's this problem.